Right, it's not a lecture, it's a class. Okay, let's record it. Okay, just a small summary. We are discussing how we can use a transition matrix. And we have introduced Russian national hero Cheburashka that can be happy or unhappy. And xt is a vector of probabilities to be in both states at time t, probability to be happy, the first one, probability to be unhappy, the second one. And I have mentioned that there are two traditions to write a vector of probabilities, like a column vector, like a row vector. I have chosen vertical tradition, but you may choose horizontal tradition. It will, okay, then you need to, that will change a little bit. So in horizontal tradition, ht plus 1, qt plus 1, we should start from, so the everything will be transposed. So it will be htut multiplied by, and here the matrix will be 0, 7, 0,
3,
0, 7. Oops, I'm mistaken in vertical tradition. Sorry. Oops. Oh, yeah. So in my case, no. It's 0, 3, 0, 5. Yeah. To have, yeah. I made a mistake. To have ht plus 1, or that's okay. Sorry, just a moment. Let's check. Ah, no. Everything is fine here. 0, 5. Yeah. 0, 3. Yeah, that was okay. But for, yeah, but for horizontal tradition, I need 0, 0, 3 here, 0, 5 there, 0, 5 there. Yeah, and I will have another condition for a matrix to be transition matrix. I need a sum by row to be 1. Okay.
yeah.
And basically, what can be done with these matrices? That's a good way to find xt. We can find, for example, what can be done. For example, we can find just let me think a little bit what can easily be done. Some example of question. Find the limit of xt as t tends to infinity. For example, we can answer a question like that. Yeah. It will be, so what is the meaning of this question? If our Cheburashka is immortal, he will never die, and he moves randomly from state to state, from happiness to unhappiness, and after his long life, what is the probability that he will be happy? So it's a limiting probability, and according to this formula, I need to calculate limits of probability matrix power t when t tends to infinity and multiply by starting probabilities. Starting probabilities are 0, 1. What is this? We know that matrix can be diagonalized. Yeah, it's like like u d u transposed. Yeah. Do you remember that? No? Oh,
Yeah.
that's enough for your question.
Last October.
Dash, we shall go on, or that's more or less enough? You have understood what is the role of transition matrix?
About this example. So what should we do next? Like how can we solve this problem?
Okay, let's solve this problem and finish with matrix. So the question is, what is the proportion of his eternal life he will be happy? Yeah. Okay, because we have discovered formula for xt, probabilities corresponding to day t. So the only thing we need is to tend t to infinity. Okay. So let's consider our matrix once again. It's 0, 7, 0, 5, 0, 3, 0, 5. What are the eigenvectors and eigenvalues? What are the eigenvalues and eigenvectors? What are the eigenvalues and eigenvectors? How do we search for eigenvalues? We subtract lambda on the main diagonal, and we calculate determinant, and we make it equal to 0. Do you remember eigenvalues?
Yes.
Okay, so in our case, that will be 0.7 minus lambda times 0.5 minus lambda minus 0.3 times 0.5 equals to 0. Lambda squared minus what? Minus 1.2 lambda. And I will have plus 0.35 minus 0.15 equals to 0. Lambda squared, if I'm not mistaken, that will be plus 0.2. Yeah.
Yeah.
Okay, so roots are by Viet theorem, they are 1 and 0.2. So you may, I will not spend time, just believe me, they are 1 and 0.2, okay?
Yeah, yeah.
Now we have found eigenvalues. We have found eigenvalues. Now we need eigenvectors. How do we search for eigenvectors? That's a good question on London exam. You have a matrix, you are
Plug in like the eigenvalues.
Yeah, probably they will not ask you about Cheburashka, but a problem with you have a matrix, find eigenvalues, find eigenvectors. That's okay. That's even for a matrix 3 by 3. That's a good example of LSE question. That's so we are working with our national hero, but the topic is close to the exam, so please be active. So yes, I understand that Cheburashka is not very not too British, but okay. So yeah, to find the eigenvectors, we should subtract lambda from the diagonal and solve the corresponding system. Yeah, do you remember? Or only Dasha remembers?
For me, I also remember.
Vika, Alexander, Mikhail,
How to
okay?
solve eigenvalues.
Yeah.
About eigenvectors.
Yeah, kind of.
Okay, let's move on to eigenvectors. I think that's from German, so they are pronounced like eigen. This is not English. This is from German, so it's not English pronunciation. Okay, so let's calculate. We have lambda equal to 1. So I take my matrix P and I subtract lambda times identity matrix, and it will be 0 0.7, 0 0.3, minus 1, 0 0.5, 0 0.5, minus 1. It will be minus 0 0.3, 0 0.5, 0 0.3, 0. Minus 0 0.5. I use Gaussian elimination, and I obtain minus.
Could you please remind me how you choose lambda?
Oh, we do not choose them. We will repeat procedure for lambda equal to 0.2. We calculate eigenvector for first eigenvalue. We calculate eigenvector for second eigenvalue. So that just we have started with that one, and we will repeat the procedure for lambda equal to 0.2. We do not choose them.
I see now.
So that's only the beginning. Okay, so I can eliminate the second equation because the second line is just a copy of the first one multiplied by minus 1. So it will be 0, 0. I will multiply by 10, minus 3, 5. And so my equation is like that, times some, I don't know, alpha 1, so maybe some x1, x2 is 0, 0. And so there are infinitely many eigenvectors. You have always infinitely many eigenvectors. You choose independent eigenvectors, but if you count the number of eigenvectors, you have always infinite number of eigenvectors. So x2 can be any real number, and x1 is just 5x2 over 3. And I have some eigenvectors like 1, 5 over 3, or 2, 10 over 3, and so on. So I have many eigenvectors. And I will choose the vector, or even a vector like that, 3, 5. I will choose a especially useful eigenvector with unit length. So all these vectors are eigenvectors, but I will choose an eigenvectors with a length 1. So if I calculate, so if this is v, if I will divide v by the length of v, then I will get 5, 3 divided by the length of this vector is 5 squared plus 3 squared is 5, 3. And here I have 25 plus 9, 34, 1 over square root of 34, I think, yeah. And it will be 5, 34, 3 over square root of 34. So that vector is especially useful. But all vectors I have mentioned, 5 over 3, 5 over 3, 1, and so on, all they are eigenvectors. Okay, any questions?
Thank you, no questions.
Okay, now we do the same thing with next lambda. Lambda equal to 0.2. I calculate p minus lambda times I. It will be 0.7 minus 0.2, 0.5, 0.3, 0.5 minus 0.3. 0.3, 0.5, 0.3. Oops, sorry, something is wrong. 0.5, 0.3. Any questions? up to now?
No.
So once again, obviously, you will have no problems about Cheburashka on external exam, but it's a typical problem. With high probability, you will have a question about eigenvalues and eigenvectors. It's a good moment to, so at first, I thought that we should move on to optimization, but at second thought, I realized that basically we need to recall something about linear algebra, and that's a good moment because it will answer the question by Dasha, and that's a good opportunity to recall about how to find eigenvectors, eigenvalues, because it's a standard question that can be encountered on exam. Okay, so I use elimination procedure, so I can multiply every line by 10. I can subtract every line from another one. So if I multiply by 10 and divide by 5, I will get 1, 1. If I work with the second line, I divide by 0, 3, I get 1, 1. If I use subtract first line from the second line, I will get 0, 0 here. Now I have a row echelon form. And if I multiply by x1, x2, I should get 0, 0. Once again, x2 is any real number, and x1 is minus x2. And I have a lot of eigenvectors, like like 1 minus 1, or 5 minus 5, or 7 minus 7, and so on. So I have an infinite amount of eigenvectors, but I will choose the most useful one, that one that has norm equal to 1. So I will divide any eigenvector by its length. So it will be minus 1, 1 divided by square root of minus 1 squared plus 1 squared. It will be minus 1, 1 divided by square root of 2. And it will be a minus 1 over square root of 2, 1 over square root of 2. So as a summary, what we have done, just let me copy, it's 5. So I will just copy to, just a moment, I will copy eigenvector 5.
Normalize eigenvectors every time.
I will explain in a moment. 5. No, it's not symmetric. So yeah, you're right. Yeah, that's useful. Yeah, you are right. It's useful for symmetric matrices, and in our case, the matrix is non-symmetric. Yeah, that was just that is a good trick for symmetric matrices, but in our case, it's non-symmetric. Okay, so I will explain why it's useful. What we have done, so as a summary, we have matrix P that is 0.7, 0.5, 0.3, 0.5. We have found first eigenvalue and many eigenvectors corresponding to this value. For example, 5, 3, 10, 6, and normalized 5 over square root of 34, 3 over square root of 34. For lambda equal to 0.2, we have a lot of eigenvectors, and we have a normalized one, like minus 1 over square root of 2, 1 over square root of 2. And we have two theorems how we can diagonalize our matrix. Yeah. So if P is symmetric, then we can diagonalize P as U times D times U transpose, where D is something like lambdas on diagonal, and U is first normalized eigenvector, and that is second normalized eigenvectors. Normalized eigenvectors. In our case, so you're right that in our case it was a little bit a waste of time because our matrix P, is it symmetric or not?
No, it's not symmetric.
Yeah, no, it's not symmetric. I haven't paid attention. Yeah, so this theorem is not applicable, and if P is not symmetric, and there are P is not symmetric n by n matrix, and there are n independent eigenvectors, then P can be diagonalized like U times D times U, and here we have -1, where D is lambda 1, 0, 0, lambda 2, and U is U1, U2, and UI are any set of independent eigenvectors. In our case, sorry, it's useful to normalize eigenvectors when we have a symmetric matrix. So we can avoid inversion because it's easier to have a transpose of matrix than inverse of matrix. In our case, P is non-symmetric, so I will take any two vectors. So I cannot use the first theorem, I will use the second one. So I will take that vector and that one, because they are easy to work with. They have no radicals, no square roots. So in my case, my matrix P.
It is an example that can probably be on the exam, or no?
Yeah, that can be, even with 3 by 3 matrix. Yeah, without Cheburashka, but with eigenvalues and eigenvectors, you can see past exams.
But this is a linear algebra. For what do we need this?
To check whether Cheburashka is happy or not.
Okay.
Are you not happy? Then we can use transition matrix. Okay, so it will be 5, 3, minus 1, 1, 1, 0, 2, 0, 0, and the 5, 3, minus 1, 1 inverse of. Yeah, am I right? This is lambda 1, this is lambda 2, this is 5, 3, minus 1, 1. Ah, yeah, I think that's okay. Sorry, I have a question in the chat. I'm happy. Oh, okay. Yeah, that's okay. We have a decomposition of matrix P, and now we go back to Cheburashka. Everything is fine up to now. We have diagonalized the matrix P.
Everything is fine.
Okay, let's move on. We have almost finished. So we have discovered that xt is P times P times P times P t times times what?
Times vector.
Which one?
Like the vector we have x0.
X0, yeah. Okay, in our case, it will be u times d times u minus 1 times, this is p, times u times d times u minus 1, this is p, times times u times d times u minus 1 times x0. Now we see that we can simplify a lot this expression, that these two matrices will cancel out. These two matrices will cancel out. That two matrices they will cancel out. Okay.
Yes, okay.
I see another ghost here. Okay, so we have u d to the power d u minus 1 x0. In our case, u is 5 3 minus 1 1, d is 1 0 0 0 2 to the power t. It will be 5 3 minus 1 1 minus 1 times 0 1. This is D, diagonal matrix. This is U. This is U minus 1. That is x0. Okay, it's easy to, if I have a diagonalized matrix, then it's easy to multiply it by itself. So basically, I have 5 minus 1, 3, 1 times 1 to the power t, 0, 0, 0, 2 to the power t, 5, 3 minus, and who remembers how can we find an inverse of a matrix? How can we find the inverse of a matrix? If you have a simple matrix like A, B, C, D, minus 1, what is the inverse?
We should write on the right-hand side the diagonal one, I think. Try to diagonalize, no, not just diagonal, yeah, diagonalize our matrix, and then take and do like the same multiplication and transformation.
You are right.
Right.
We write it like this, and we do some Gauss transformations. We obtain identity matrix on the left, and on the right you will have the inverse of. Oh, here we have the answer. Yeah, that's one way. Or we will use. I will not. I will use the to save time and to speak a little bit about optimization. I will use the final answer, so it may be like 1 over determinant of the original matrix times I interchange. So there is a final answer that you need to interchange elements on the main diagonal and multiply by -1 elements on the second diagonal, and it will be like dA minus B minus B. So that's the final answer. And in my case, I will have 1, 5, 1 minus 3, and I need to divide by determinant, and determinant is 5 plus 3. Okay,
Okay.
And finally, I can find the limit when t tends to infinity, xt. So in what state Cheburashka will be after a lot of years after his birth. And if I calculate this limit, I will obtain 5 minus 1, 3, 1, 1, 0, 0, 0, 1 over 8, 1, 1 minus 3, 5, 0, 1. Because 1 to any power will be 1, and 0.2, if I multiply 0.2 a lot of times by itself, I will get eventually 0. Any questions? And finally, we have solved the Cheburashka problem. We just need to multiply these matrices. If I multiply these two matrices, I will have 1, 5, 1 over 8. If I multiply these two matrices, I will have 0, 0 here. And 5, 3 here. And finally, we get 5 over 8, 3 over 8. And these are honest probabilities. They sum up to 1. And basically, we have solved, we have used transitional matrices to discover the fate of Cheburashka. Cheburashka will spend 5 among average 8 days, 5 days he will be happy, and 3 days on average out of 8 days he will be unhappy. Okay?
Sorry, I have a question for this about happy or not. Because for probability, he must be happy or not very happy. It means the probability for the consequence is 1. But how do we make sure the proportion for this action is the same as 0?
I don't get your point. We have proven everything. We have done everything without any assumptions. So we have started from, so what was our, so we started with a question by Dasha, how do we use transition matrix? And I have provided an example of Cheburashka, who can be in 2 states. I have described his what can happen with Cheburashka in 1 day is described by this matrix expression. So vector T probabilities are multiplied by a matrix to obtain vector of probabilities that correspond to day T plus 1. Then we have used the standard procedure. This is a matrix P, and a typical exercise that is very often encountered on the exam. You have a matrix P, find its eigenvalues, eigenvectors, and diagonalize P. That is a typical exercise from external exam. That's okay. Eigenvalues, eigenvectors, diagonalize P. So we have this is standard exercise. So we have transformed after this exercise, we have transformed P into a product of 3 matrices. Now we have calculated the vector of probabilities. That is the vector of probabilities that corresponds to day T. And we have an expression for this vector. It's along with matrices, but that's a correct expression for the t probabilities. And then the question I have proposed is to calculate the fate of Cheburashka after a lot of time after his birth. So imagine that 100 years has elapsed and Cheburashka is mature and what is the probability that he is in happy state now? And the probability is approximately 5/8 because the limit is 5/8. Okay?
Thank you. It's okay.
Dasha, are you happy with the use of the
Yeah,
transition matrix?
kind of.
Okay, so how we use transition matrix? So to calculate probabilities, sometimes to calculate expected values. To calculate probabilities with transition matrix, we need sometimes diagonalization. And so sometimes we need eigenvectors and eigenvalues. Okay, we have done that problem. Any more questions?
Thank you. No questions.
Okay, so let's what we can do? Oh, okay, let's do some optimization with graphical methods. We have a little bit of time, so let's solve some linear programming. Or maybe let's solve something from our past example. Let's solve something from we have solved something that is probably encountered on external exam, and let's solve something. Just a moment, I will find something. Okay, I think I have found also that where is the problem I would like? Okay, yeah, just a moment. Oh, this is too long because I'd like to finish in 20 minutes. Just 30 seconds and I will find something that can be solved. Yeah, I like this. So it's an exam a problem like that, we need to maximize 3x1 times x2 minus x3 x2 cube. We need to maximize it. And we have a lot of constraints. We have 2x1 plus 5x2 is greater than 20. x1 minus 2x2 is less than 5. And x1, x2 are greater than 0. And it's required that we check in DCQ. So there are many ways to solve this problem. It's problem number 1. But there are many ways. We may solve it without Lagrangian function, or we may solve it with Lagrangian function. So there are many ways to do it. So if I will do both. I think I have enough time. So if I'm not case A, I have no limits. My first idea that if you have no requirement to use Lagrangian function, then simplify the problem as possible. So that's my main advice. So if there are no restriction in the text, simplify, simplify, simplify. In my case, if I have no restrictions, then I will just say x1 is 2x2 plus 5. I will plug in my equation. So I will maximize what? I will maximize 2x2 plus 5 times x2 minus x2 cube, subject to what? Subject to 2 times 2x2 plus 5 plus 5x2 is greater or equal than 20. The second one is automatically satisfied, and 2 more restrictions. 2x2 plus 5 is greater than 0, x2 is greater than 0. So if I'm not obliged to use Lagrangian function, I will simplify as much as possible. Okay?
Okay.
So the first idea, check what is required. I need to maximize the function. If I have only 1 or 2 variables, my advice is that in that case, it's better to solve it graphically if this way of solution is allowed on the exam. Sometimes you have a requirement that use Lagrangian function or and the method is prohibited. Because in that case, I can draw this function and I can easily solve. So if I have no requirement, then I just say I need to maximize 6x2 squared plus 15x2 minus x2 cube. And I have requirements like, if I simplify it, will be 4x2 plus 5x2, 9x2 is greater than 10. 2x2 is greater than plus 5 is greater than 0, and x2 is greater than 0. Among these 3 conditions, which one is the more restrictive one, is the most restrictive one? The first, the second, or the third? Which one is the most restrictive?
The third one.
Oh, but be careful. The first one says x2 is greater than 10 over 9. The second one says x2 is greater than minus 5 over 2. The third one says x2 is greater or equal than 0. And the most restrictive one is the first one. Yeah, because if number is greater than 10 over 9, then it's greater than 0. The second one and the third one are automatically satisfied if the first one is satisfied. And in my case, I will maximize 6x2 squared plus 15x2 minus x2 cube, subject to x2 is greater than 10 over 9. So I have a very simple problem. I have not used in Lagrangian, I haven't used Lagrangian function. So I will just try to plot this. If my function is f of x, I will emit index 2, 6x squared plus 15x minus x cube. If I take the derivative of this function, it will be 12x plus 15 minus x squared. The roots of this function are, I think, what are the roots of this function? What are the roots? F prime is 0. 12x plus 15 minus x squared is 0. X squared minus 12x plus 15 is 0. What are the roots? I think they are not too beautiful, but anyway, x is equal to, so discriminant over 4 is 6 squared minus 6 squared minus 15. And it's 21. And I get the solution that is 6 plus or minus square root of 21. Any questions?
Thank you, no question.
Should I wait a little bit?
I think we can go on.
Okay, but basically we have finished. So what are these numbers? Approximately x, that is equal to 6 plus square root of 21, that is approximately how much? Approximately, not exactly. Square root of 21 is a little bit bigger than woohoo! Who is with me? Or you are just are you trying to solve, or you are just listening what will happen?
Sorry, I tried to talk to you, but because the microphone is muted, the 21 squared is bigger than 16, less than 25, so it's around 45.
Yeah, you're right. So basically, that is roughly 10, and it's a little bit more than 10. Yeah, I will write it like 10 plus small delta. If I consider x that is 6 minus square root of 21, it will be like 1 plus delta. Yeah, and I need to check. So the tricky, the tricky point in this problem is to find which one is bigger. The second root, x2, or 10/9. So let's check this tricky place. What is bigger, 10/9 or 6 minus square root of 21? So I multiply by 9. I have 10, 54 minus 9 square root of 21. I have 9 square root of 21, and here I have 44. And if I take the square, if I will square these numbers, I will have 81 times 21 over 44 squared. Yeah. And which one is bigger?
The second one is bigger.
So it's 80 plus 1 times 20 plus 1 over 40 plus 4 squared. And I will get, that is 1,600 plus 20 plus 80 plus 1, and that will be 1,600 plus 40 plus 4 squared. Yeah. And I see that which one is bigger?
The second one is bigger.
Why?
First one, of course, first one is bigger.
This will appear, that will disappear, and 20 plus 1 is bigger than 4 squared. So that is bigger than 6 minus square root of 21. So now I can plot my function f of x. F of x, I remind you that my function was 6x squared plus 15x, 6x squared plus 15x minus x cubed. What do we know? We need to plot, this is 0, this is 10/9. We know that there are 2 points where the derivative is 0. The first point is x1 is 6 plus square root of 21. The second point is a little bit, so I will sketch like the difference is big, but on the real picture, this difference is very small. Very small. And nevertheless, I can draw the function, and that will be enough to solve the problem. So these are 2 points, x1 and x2 are 2 points where the derivative is 0. The second derivative is f prime prime is what is 12 minus 6x, and I see that the second derivative at the point at the rightmost point, it is negative. Here the second derivative is positive. So if the second derivative is positive, I have a maximum. If the second derivative is negative, so in that case, I have a minimum, and in that case, I have a maximum. So I can draw the parabola, sorry, not parabola, a function roughly. And the rough sketch is something like positive second derivative, so it's something like that. Negative second derivative is something like that. And finally, I draw the function. The function goes like that. and I need to maximize my function. I need to maximize f of x in that region. And I clearly see that the best point x star is which one?
Is the second one?
Yeah, is 6 plus square root of 21. And basically we are happy. We have solved the problem. That is. Okay, any questions?
Thank you. No questions.
That's all for today. So my advice is the following. If you have a maximization, minimization problem, first read what you are allowed to use. If you have no restrictions about which method to use, if you have one or two variables, then go for sketch. That will be much faster and you will write the Lagrangian function, because honestly, for this function, if you do not simplify the problem, you will have a Lagrangian function with 3 lambdas. Yes, you can go with 3 lambdas and build the system to solve first order condition, but it would be tough. My advice is check what is allowed, what is not allowed in the problem, and go for the simplest way. So thank you for coming. Have a nice day. Yeah.
See you after 20 minutes. That will be boring. Thank you.
Yeah. Bye-bye.
Bye-bye.